I will start with more problems from the center of mass. Now, suppose, for example, we have number 34. Should I do number 34? Or maybe number 40, by the way. Number 40. I'll do number 40. We have this situation here. Let's do one, so approximately this, and then the triangle. The idea is find center of mass by the centroid without integration. Find the centroid without integration. Okay. If we look back into my explanation last time, if you have a rectangle, then the centroid is actually located right in the middle. It's right in the middle. Okay, that's where the centroid is. If we have a triangle, no, it's not where. If we have a triangle, any random triangle, then the centroid is located at the average of the coordinate. The centroid is located at the average of the coordinates. So I'm saying this, the following. So let's say this is 0, 0, okay, and this is A, comma 0. This is 0, comma B, and this is A, comma B. Okay, now then the center of mass here will be A over 2, B over 2. You see what I mean? Okay, which is actually just the average of all those four sides. Which is just the average of all those four sides. If you add all the coordinates, right? Suppose 0, 0 plus A, 0 plus 0, B plus A, B, all of them divided by 4. Then you will get 2A, comma 2B divided by 4. That's A over 2, B over 2. Okay, now if you have a triangle, let's say this is 0, 0, for sake of simplicity, okay? I use 0, 0 there, and this is A, comma 0, and this is B, comma C. Then the center of mass will be the average of those three coordinates. Okay, when you add, you will get 0 plus A plus B, comma C over 3. There are three coordinates there, right? Okay, so it will be A plus B over 3, C over 3. Okay, that actually works for every polygon. Okay, now then, if you see these coordinates of the of this polygon here, you have -1, 0. Of course, this then -1, 2. Okay, this is 0, 2. Okay, this is -1, 0, and this is 2, 0. Where is the center of mass for this? Just the average of them. Okay, the centroid will be, remember when I use the word centroid, it means the density here is uniform. Like when you laminate, right? It's basically a piece of paper or a piece of plastic. Okay, the centroid will be -1 plus -1 plus 0 plus 2. That's for the x component. For the y component, 0 plus 2 plus 2 plus 0. All over divided by 4, because there are 4 coordinates. And the centroid will be 0, 1. The centroid will be 0, 1 here. I don't like that though. I don't think that's correct. Oh, no, I don't think that's correct. I don't think that's correct. I don't like that, but yeah, again, I don't think that's correct. Do you know why I say I don't think that's correct? Yeah, it's supposed to be lower. It's supposed to be lower. Do I make a wrong coordinate somewhere? Okay, let's not doing it this way then. But what I did, I kind of like, okay, what I did here in blue is correct. What I did here in blue is correct. This is correct. Nothing wrong here. Yeah, nothing wrong there. Sorry. I want to erase this. No. So, yeah, I look at that right away. I know that's not right. I believe it is 0, something. I believe it is 0, something. But I was not sure with. Yeah, I was not sure with the y part. Yeah, we need to do it separately. We need to do it separately and then get the average of those two. You're right. That's actually the proper way to do it. I tried to shortcut that. Okay, so the center of mass for the first one is here. I tried to erase this red one, this red dot here. No. I just leave it. I will just leave that red dot there. Okay, so the first one is here, right? Okay, while the second one is somewhere here. So the centroid of the rectangle will be, what's that? That's -1/2, 1. Okay, while the centroid of the triangle that will be 2/3 over 2/3, 2/3, 2/3. If you full highlighter over red dot, what happens? The things it's highlight, so it's not, it doesn't work. You see, I highlight that, no, it doesn't work. Well, anyway, then we will get the average of this. The average together with the area though. Okay, the average together with the area. So the area for this, the area for that rectangle is 2. The area for that triangle is also 2. You see, right? Okay, so the centroid, total centroid of this region here will be 2 times negative 1/2 comma 1 plus 2 times 2/3. So that will be negative 1 plus 4/3 comma 2 plus, no, that's not supposed to be, over 4, over 4. All of them over 4, the total area. Negative 1/2. Yeah. The centroid for this, for the rectangle. The centroid for the rectangle is negative 1/2 comma 1. It's between negative 1 and 0, negative 1/2, and the height is half of that 2. Okay, what will this be? This will be 1/3 over 4. That's 1 over 12. Oh wow, very close to 0. And then 1/2 plus 1/3, that would be 5, 6. Okay, number 41, for example, which is kind of fun for me. Number 41, we have this shape. And then copy that. And a rectangle. Let's say something like this. Okay, by symmetry, I can say that the x bar will be 0. Agree? By symmetry. This is 1, 2. This is 2, 0. This is negative 1, 2. This is negative 2, 0. This is negative 2, negative 1. This is 2, negative 1. Yeah, the center of mass will be, for the x bar will be 0. So that way we can worry only for the y bar. Now, as for the y bar, the y component for this will be what? Something 2/3, right? The one here is something 2/3 also. Okay, and while this one must be 0, negative 1. Right? Now the area of the rectangle is 4. Is it? Yeah, it's 4. The area of each triangle is 2 times 2 divided by 2. So triangle 1, the area of triangle 2, also 2. So the y bar will be 1 over 2 plus 2 plus 4. That's the total mass multiplied by the first triangle y bar plus the second triangle times y bar times its y bar plus 4 times the y bar of the rectangle. So that's 8 over 3 minus 4. That's 1/3 minus 1/2. That's negative 1 over 6. So the centroid is 0, negative 1 over 6. Let me cheat. Long time not cheating from the back of the book. It feels so good if you get it right? If you get it wrong, it feels so bad. What number is that? 41. Eh? No, I got it wrong. It's 0, 1 over 12. I got it wrong. It's 0, 1 over 12. It's not 1. Oh, I see. I make mistake here. This is negative 1/2. My bad. That's negative 1/2. So this should be negative 1/2. So this is minus 2. So this is over 4. Now that's the 1 over 12. Yeah, I made mistake here earlier. I think somebody warned me about that, huh? Yeah, it's negative 1/2. Thank you, Anthony. I was not aware with what you said negative 1/2 earlier. Now I realize that. Thank you. So that's the mistake I made. The correction happens here. Boom, 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 boom. Okay, that's 1 over 12. Okay, that's the center of mass thingy. How about let's say we do number 10, hydrostatic force. So we have water, and you submerge a square diagonally into the water vertically. So imagine if you have a square, right? Imagine if you have a square that you rotate. Okay, and then you put it there. You see what I mean? And the sides of that square is A. Or you can imagine if at the wall of a pool you have that kind of hole, then how big is the hydrostatic force against that hole? If you want to cover that square, the whole square hole with let's say with some cardboard, will the cardboard sustain the water pressure? Okay. Now then, if we have this, can you compute how far do you need to go below the water? By Pythagorean theorem, this is a square root of 2, agree? Right? And when you go this far, the width is twice of that. The width is twice of that. But this is not twice of that. Uh-oh. So where should I do my reference? Where should I do my reference? This is, the depth here is a square root of 2 over 2. So the width is increasing until you have square root of 2, or a times square root of 2 over 2. But then from here on, it's actually decreasing down to 0. So what is the hydrostatic force? The force will be rho g times integral from 0 to a radical 2 over 2. If this is my reference point, if my reference is here, if my reference is here, this is my x equals to 0, then when the depth is x, the width is twice of that. And when the width is x, the width is twice of that. Plus integral from, let's say from this one here. Do you want to use the same x? Let me use y. So let's say this is y equals to 0. Let's say this is my y equals to 0. So my y will be moving from 0 to a square root of 2 over 2. My y will be from here to here. Okay, so for each y, my depth will be a square root of 2 minus y. That's my depth. And the width will be 2y. Okay, that's it. Does it make sense for you? The thing is, if I set it up this way, it seems like something cancels nicely though. This is rho g integral from 0 to a radical 2 over 2 2x squared plus dx plus integral from 0 to a radical 2 over 2 2a radical 2y dy, and then minus integral from 0 to a radical 2 over 2 2y squared dy. Now the thing is, these two guys here cancel each other. This guy and this guy cancel. Right? So I get rho g times a radical 2 y squared from 0 to A radical 2 over 2. That's rho G A radical 2 A squared over 2. The thing is, this is too easy such that I question myself if I did it right. I'm looking for a better question. Maybe number 12. Maybe number 12. I'm kind of having fun with this. Number 12. A milk truck carries milk with density. Oh, they tell us the rho. The density is 64.6 pound per feet cube. Okay. In a horizontal cylindrical tank with diameter 6 feet. Approximately that. And then they say that this is 6 feet. Okay. Part A, find the force exerted by the milk on one end of the tank when the tank is full. So basically we look at that circle, this to be more precise. Okay. And then you have radius, I'm sorry, the diameter is 6 feet, so the radius is only 3 feet here. Now you fill it full with milk. The question is then, what is the hydrostatic force of that milk against the end of that truck, whose shape is a circle? I think I will do my point of reference. I think I want to do my point of reference right at the center of that circle. So if this is x equals to 0, then my x will move from x equals to -3 to +3. Maybe -3 here to +3 here, because the depth is increasing, right? It's getting deeper and deeper. Okay, now then, if my x is here, if this is my x, then what is the width? It will be twice of this. But that is equal to square root of 9 minus x squared. Okay, notice that it is still consistent when my x is negative, right? If when my x is negative, then the length here is still square root of 9 minus x squared. Okay. So let's say when the depth is x plus 3, okay, because the depth is, if this is x, you need to add this 3, is it right? When the depth is x plus 3, the width is 2 times square root of 9 minus x squared. The integral will be from -3 to 3. Let's do it. So the hydrostatic force will be rho g integral from -3 to 3 x plus 3 to square root of 9 minus x squared dx. Okay, they tell us the rho, but I will just leave it like that until very end. I don't want to get my headache with that ugly number. Just leave it as a rho, just in case all of a sudden Thomas changed his mind. You know what? I don't like milk. I want vodka. Okay, fine. Then change that, rho. Okay, now then how do we compute this? Try to benefit from the pattern of that integral. This is rho g times integral -3 to 3 x times square root of 2 times square root of 9 minus x squared plus, so I distribute this guy against x and against 3. Is it okay? Plus integral dx plus integral from -3 to 3 of 6 square root of 9 minus x squared dx. Okay, so this guy here is equal to 0. While this guy here is 6 times pi r squared over 2. So the answer is 27 pi rho g. The question is, you need to answer this though. Why is this here? Why is this here? Anybody can tell me? Why they cancel out? Yeah, they cancel out, but why? 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 Yeah, it's one thing about symmetric, but there's one more thing. It has to be symmetric n. Symmetric interval. Huh? Odd function, that's right. Because if that's even function, you need to double it instead. Okay, so the reasoning is actually integral over symmetric interval of odd function. Okay, now another one is, can you tell me how did Thomas do it so effing fast? You can ignore the 6. The 6 was there already, so it's not really about the 6. That's right. That's the area of half circle. So honestly, one way, to be honest with you, one way for me to check if you pass your calculus 1 the right way, it's an Eiffel Thomas, right? If I want to check if you pass calc 1 the right way, and not repeating, how to is by asking you this question. Let's say integral from 0 to 2 of square root of 4 minus x squared dx. Ask you that question. Okay, whoever does this using trig substitution, that person is repeating how to. Because we learn trig substitution in chapter 7, not even chapter 6, definitely not chapter 5 or below. So once that person used trig substitution, that person is repeating the class. Okay. Now, of course, some students don't know how to do this at all. They just, well, I don't know how to do it. Then you don't even know what integral means. But those who knows how to do it, those comes with understanding, will be able to see that this is actually the area of quarter circle with radius 2. So the area is pi r squared over 4. That's equals to pi. Bang! Any computation? No. Just look at the graph. Okay. Now the thing is, let's make this question even more interesting. This is only part A. Let's do part B then. Let's do part B. Let's do part B first. Suppose then it is half full. Suppose it is half full. So the milk is half full. Don't divide it by 2. You cannot divide it by 2. Okay, you cannot divide it by 2. So let's say this is my x equals to 0. As I go down x unit, the width will be 2 square root of 9 minus x squared. Okay, so the hydrostatic force of this milk will be rho g integral from 0 to 3. The depth is x. The width is 2 square root of 9 minus x squared dx. Just regular substitution, huh? U equals to 9 minus x squared, so u equals to negative 2x dx. So this is my negative du. This is c, oh no, I'm sorry, this is 9 and this is 0. So that's u to the power of 1/2 negative. Refers the order of integration, the limit of integration to get what I like to see. That's rho g times 2/3 u to the power of 3/2 from 0 to 9. That's rho g 2/3. That's 9 times 3, 27. Times 27. So that's 18. Rho g. No pi, huh? Surprise. Surprise, no pi. Now, what we did earlier is basically the same to do the following. What we did earlier is the same to do the following. If I have water, I try to teach you something our textbook does not teach, but this is also useful if you are going to civil engineering. Okay, so what happened earlier, you basically have a circle that you submerge for part A, a circle like that, right? A circle like that. Now imagine if I sink this circle even further down. Imagine if I sink this circle further down. Let's say I sink that by a unit down. By a unit down. Remember the radius is 3, right? Okay, the radius is 3. Okay, and we have computed earlier what we have there. The hydrostatic force is, what's that again? 27 pi. 27 pi rho g. Now suppose I submerge that by factor of 8. Suppose I submerge that by factor of 8. So my new line, let me do the little transformation. So let me make my x equals to 0 here. So the hydrostatic force, I now use the blue color, that's rho g. I'm sorry. No, that's not there. My bad, not there. My x equals 0 should be, now my originally x equals to 0 was here, right? That's my original x equals to 0. Now I will move my x equals to 0 here. That's my line of reference. So my integral will be integral from -3 to 3. The depth will be a plus 3 plus x. Because here the depth was x. I'm sorry, the depth here is 3. Right? Let's see the setup. Original setup there is f equals to rho g integral from -3 to 3 of 3 plus x to square root of 9 minus x squared dx. That's what we had earlier. Right? Now I move my reference x equals to 0 down by a units. So my integral of my depth right now, this guy, the depth increased by a. Right? But the width functions actually stay the same. 2 radical 9 minus x squared dx. Okay. Now we have computed this earlier, rho g. Let me split this integral. Integral -3 to 3 of 2a square root of 9 minus x squared dx plus integral -3 to 3 of 3 plus x 2 square root of 9 minus x squared dx. We know this guy here was what again? What is that again? Let's see. That's 27 pi. Is that right? That gives us 27 pi. But what is this? What is this here? Notice I can factor the a out. Right? And what is this? What is this here? That's the area of the circle. Okay? as if I'm saying the following, as if I'm saying that if you have a circle with hydrostatic pressure, hydrostatic force 27 pi rho g, and the area of that circle is A, then when you submerge that by factor of by a unit down, then the hydrostatic pressure will be the same 27 pi rho g plus the area of that lamina times how deep you push it in times rho g. Okay, so this is the extra hydrostatic pressure because you push that further in. Okay, that's why, for example, if you try to do question number 3, question number three has the following situation. You have a rectangle. This is 4, this is 6, you submerge that by 2. Right? Okay. Take a look on the setup. If this is my x equals to 0, okay, if that's my x equals to 0, then hydrostatic force will be rho g integral from 0 to 4 because the depth increased by 4, right? And for every x you choose here, the depth is x plus 2. And the width is 6 dx. Okay, now which is equal to rho g integral from 0 to 4 of x times 6 dx. Notice that this is basically the expression, the integral expression, if your water is actually here. Okay, if your water is actually there, plus rho g integral from 0 to 4 times 2 times 6 dx. But this guy here is basically rho g times how far you push it, and that would be 24. That's the area of that rectangle. Okay, so let me picture this. This is the situation if you have the rectangle actually submerged right at the edge of that rectangle. Okay, wow, I spent so much time, 15 minutes for this extra stuff. Well, anyway, I have fun. But this is the thing that our textbook doesn't say, though. This is the thing that our textbook doesn't say. Okay, now let's go on to chapter 10. 10.1 parametric equation. 10.1 parametric equation. Is chapter 10 in your next exam? No, your test 2 only up to 8.3. So your test 2, your test 2 material will be from 7.4. From 7.4. Oh, let me see further because I skip a lot of sections. 7.5, 7.8. And then 8.1 to 8.3. Okay, the thing is, even though I say it's only start from 7.4, 7.5 is technique of integration as a summary. So you basically need to know all the integral prior to 7.4 anyway. Okay. I'm sorry, but yeah, that's basically what it means. You need to know all the technique of integrations prior to test 1 anyway. Should not forget them. 8.1 to 8.3 is more into setting up the integral. Chapter 10, parametric equation. 10.1, I mean. 10.1 parametric equation. Parametric equation in 2 dimension is given by x as a function of t, y as a function of t. Our textbook, they don't want to use x and y as a function of t, they use f and g. So our textbook say it this way, x equals to ft, the y is a function of t. But that notation actually the same meaning with this. That's the same meaning. X as a function of t, y also a function of t. Now, I don't have any plan to do this section fast. Instead, I want you to be at least stronger because we have this parametric equation in Calculus 3, and it's basically 1 chapter. And parametric equation, parametric function in 3 dimensions is so crucial. And when I taught Calculus 3, I always have issue with students who don't even know what is parametric equation. They could not even do 2 dimension, not to say 3 dimension. So parametric equation is supposed to be something you have learned in trigonometry in our class, but I'm aware trigonometry class in our college, but I'm aware a lot of you didn't take trigonometry with us. So more or less, I basically need to repeat what I taught in my trigonometry class here. I will start with doing an example to build your intuition. Okay. Example 1. Example 1. Let x equals to 2, maybe not 2t. Let x equals to t, and y equals to 2t minus 1. Suppose I sketch this graph. Suppose I try to sketch this graph, then I will do a 3-column table. T, which gives us x and y. So for example, when t equals to 0, x is 0, y is -1. When t is 1, x is 1, y also 1. When t is 2, x is 2, y is 3, and so on and so forth. Okay, now let me sketch the graph. When t is 0, x is 0, y is -1. When t is 1, x is 1, oops. When t is 1, x is 1, y is 1. And so on and so forth. Oh, it looks like that, huh? Thomas, I see x equals to t. So when I substitute that t here by x, I get y equals to 2x minus 1. So can I just do it that way, that I do substitution and I get that line? Yeah, you can. You can. Actually, that's one of the technique to graph that we will learn later on. But I don't want to get rid of the t too early right now, because I want to. I would like you to realize that. Oops, I want you to realize that the reason we use t in parametric equation, because it has something to do later on with the idea of time. So let's say this parametric equation is the trajectory, or the, you know what is trajectory? The path of a certain satellite or certain item or car moving at time t. Okay, so when t equals to 0, that stone is located here, or that car is located here. When t equals to 1, it is located here. T equals to 2 is located here. T equals to 3, it's located there. Okay, the trajectory, the path, form a line. But on the top of the shape, it also gives us the timing. Okay, instead of just to give us the shape, it also tells us the timing. At what time, where is that thing located? Okay, that's actually the main use of parametric equation. Okay, now of course we assume that the time starts from 0, but if the time starts from -1 and on, like you can go to the negative region, then you go there this way, right, where the t -1 is here, for example. Of course, this example is a very easy example. It's an easy example. What I try to show you from this example is the following. One of the technique we will use later on is called parameter, eliminate the parameter. You eliminate the parameter, you do substitution. That's one. But the additional ingredient we put into this parametric equation is the fact that we have the sense of time. Okay, in calculus 3, we have this question here, this type of situation. If you look at my teaching experience, you see that I teach calculus 3 more than calculus 2. Now, here's the thing though. Here's the thing. Imagine if my car, I drive this way, and you drive this way. Do we have accident? Simply because of our path intersecting doesn't mean we have accident. Why? Because by the time you reach here, I'm already there. Imagine the intersection with traffic light. Okay? You go this way. I go this way. Why don't we have accident? We don't have accident because we never reach the same point at the same time. You have that accident because you are at the same place at the same time. Okay, so when you have an accident, if you bump into somebody, blame that person. Okay, why do you take this place at the same time I do? Because if you come after I leave, then there should not be any accident, right? Okay, the problem is you hit the same place at the same time. The same time is the issue. Okay, so we have common point, we have intersection. Okay, but simply because our path is intersecting doesn't mean we intersect. Now, somebody told me that in a couple of days the Earth will have some meteor actually hit the Earth in a couple of days. Why? Because they already have that trajectory of that meteor, and then they construct the trajectory, and it happens that the Earth will hit the same point at the same time. Okay, nobody will worry if this goes there while I'm still here, or if I'm already there. Then I don't worry about that meteor, right? We worry because the size is like quite big. I think it's like the radius is around 1 or 2 miles, maybe even 3 miles. Yes, it will burn when it gets to our atmosphere, but imagine the speed though. The speed is like 80,000 kilometers per hour move. Okay. With that speed, let's make it 800 kilometers per hour. With that speed, whatever hit you, it will create a hole on your body. You don't believe me? Create a fly, a little fly. Okay, but let it fly so fast into your face. It will create a hole. The thing is, this is, as I know, faster than a bullet. But don't worry, Thomas. The fly will crush itself on my face. I don't think so. Don't assume too much. Okay. How do you know that the fly's face is softer than your face? How do you know? Okay. Unless you really believe that your face is so thick, right? No pun intended. Okay. Challenger, the shuttle that explodes. It explodes because it has some condensation, and it has some ice that hits the wing. The wing is definitely a lot stronger than the ice. But the thing is, they were moving so fast such that that little ice, when it hits the wing, it kind of like the thermal coat that it has becomes dink. It dink and becomes a hole, and the atmosphere actually burning it. Okay, so don't underestimate a fly if it flies at such a high speed. Now, I'm trying to prepare you if you are going to aerospace engineering. No, not aerospace engineering. More into what's that? What kind of physics is that? I forgot the name. Astrophysics. Okay, aerospace engineering, that you go to outer space. SpaceX, yeah. So, do you know that I have 3 students actually working at SpaceX? In fact, I have 1 student already working at Raytheon, I think around 4 years ago. Already worked at Raytheon and purposely took Calculus 3 from me. He said, Thomas, I just heard from my office mate that he learns a lot in Calculus 3 from you. And well, he got an A in my class. Okay, but I myself actually appreciate him because he really brought, when he did my problem, he understand a lot of physics behind it, while I only taught math, I only taught the math part, but then he can actually bring the trajectory thing there. By the way, yeah, I hope one day I have a chance to teach Calculus 3 again. They assign me to teach Calculus 3, but every time they see students see my name, they drop the class. They actually say, oh, you know what? I register for somebody else. Let's do another example. Let's say I have x equals to 2t, and then y equals to t squared minus 3. So when t equals to 0, the way you sketch that, when t equals to 0, what happened to the x, what happened to the y? When t equals to 1, the x will be 2, and this will be negative 2. T equals to 2, this is 4, this is 1, and so on and so forth. Okay, now if you want to see the path, if you want to see what the graph look like, then you can do elimination. Okay, so x over 2 equals to t, and then you substitute that, you get y equals to x over 2 squared minus 3. So that's x squared over 4 minus 3. So the path will look like this parabola, or go down 3 units better. So approximate. Okay, which when t equals to 0, it's located here. When t equals to 1, it's 2 comma negative 2. I'm sorry, this is t equals to 0. T equals to 1. When t equals to 2, it's here. So in other words, if this were the trajectory or the path of a fly, okay, then this fly actually crossed the x-axis sometime between the first and the second, or maybe the first or the second unit of time. Somewhere in between, it crossed the x-axis. Okay, but be a bit careful that doing parametric elimination, eliminate the parameter, may give you a misleading curve. Let me give you an example here. I hope this example is simple enough. Let's say my x equals to sine t, my y equals to sine t. Then you say, oh, sine t equals to x, sine t equals to y, therefore x equals to y. And from there you say, oh, then the sketch of the graph will be this diagonal line. What's wrong with this? What's wrong with this argument? Something to do with the domain of t. Something to do with the domain of sine t. Okay, and the range of sine t. Even though when you do parameters elimination, you get y equals to x, but in reality, if you think about it, x will never be more than 1 and never be less than negative 1. Okay, at the same time, we know x equals to y. So in reality, the graph will only be this segment. Will only be this segment. So when you do parametric elimination, you eliminate the parameter, okay, the resulting graph contains the actual graph. You need to then go deeper and see the domain or the range of the function you eliminate. Okay, it's not the whole line. It's not the whole line from negative infinity to infinity here. No, it's not. It's not. Okay, you can see that sine t only oscillate between negative 1 to 1. Oh, so Thomas, hold on. So you are saying the graph of this function, this parametric equation there, the graph is only like this. Yes, It's finite. The length is finite. But how come? But how come? The thing is the t actually moved from negative infinity to infinity. You don't say anything about the t terms. Yeah, it's fine. The thing is like when t equals to 0, the coordinate is 0, 0. When t is pi over 2, actually it's moving there. When t is pi, it's going back here. When t is 3 pi over 2, is going here. So basically, this parametric equation here will create a busy guy going back and forth this way. You see? But they will not go past this 1, 1, and will not go past this negative 1, negative 1. Okay, again, let me write it as a note. The graph of a parametric equation is part of, maybe the whole, but maybe just part of the graph of the equation resulted from or obtained from parameter elimination. Actually, I can change that x equals to sine t into this one, for example. Can you tell what's the graph of this look like? X equals to e to the t, y equals to e to the t. What will the graph of this look like? Yeah, when we do parametric elimination and y equals to x. Now, the thing is, when you eliminate the parameter, the resulting graph is more than what you need. Y equals to x is something looks like this. Okay, but the y is greater than 0. That's right. Okay, the y, actually both of them, x equals to y, but both of them will be greater than 0. It will never be 0. So the actual graph is, let me use in blue, the actual graph is this. The actual graph is something looks like this. That's what the actual graph looks like. In other words, however far to the left your t, let's say t negative 10,000, t is negative 1 million, it will never reach origin. It will never touch origin. And the difference between this parametric equation you may say, oh, the graph of this curve here is the same to the graph of this curve. Y equals to t, x equals to t, y equals to t for t greater than 0. The path will be the same, but the timing is different. The timing is different. What's the difference? Okay, when t is equal to 1, for this guy here, when t equals to 1 is 1, 1, 2, 2, 3, 3, and so on and so forth, right? When t is 1, 2, 3, 4. But for this guy here, when t equals to 1 is already here, t equals to 2 is here, 3 equals to 3 there. It's actually shooting in that direction a lot faster. It's increasing exponentially, while this one only moves linearly. Okay, so even though it goes to the same path, It goes through the same path. It goes through that path at different speed. Okay, that's what makes parametric equation so special to study. It incorporates the time idea into that equation. Now, our textbook does not talk about the t as a time yet, but we will see that later on in calculus 3. Okay, now I will give myself a little break. You don't need to take your break if you don't want to. And then when we come back, we will explore more parametric equation. And we may be able to try to graph some of them. Okay, let's come back at, right now is 8:36. Let's come back at 8:47. One of the basic, another basic parametric function, parametric equation you need to know is this one. X equals to cosine t, y equals to sine t. Why they are important? Because one way to eliminate the parameter is by seeing x squared plus y squared equals to 1. Right? So this parametric equation will give you a circle with radius 1. In fact, we can trace it with when t equals to 0. When t equals to 0, so basically, maybe I put it this way. When t equals to 0, the cosine t, which is the x, is 1. The y, which is the sine t, is 0. When t equals to pi over 2, this is 0, this is 1. So when t equals to 0, it's here. When t equals to pi over 2 is here. When t equals to pi is here, and so on and so forth. From here, we see that not only the path, we also see the timing, and therefore we see the direction of how the point actually moving. Okay, now we may have the same graph using different parameterization. Suppose I change that into x equals to sine t, cosine t, y equals to cosine. See, you still get the same graph, right? When you try to sketch the graph of this parametric equation, you will still have the same graph, but the difference is at different time, it may be at different point. For example, when t equals to 0, the y is when t equals to 0, the y is 1, but the x is 0. So when t equals 0, it's here. When t equals to pi over 2, it will be here. This is when t equals to pi. So it goes this direction. Okay. The same shape, different direction of trajectory. Okay. Now, can you imagine what happened if I make it like this? So I use example 1c here because it is related to example 1, example 1a. Suppose I make it x equals to 3 cosine t, y equals to 2 sine t. I want you to remember our example 1a is this: x equals to cosine t, y equals to sine t. That gives us a unit circle. But what happened when I put 3 in front of the x and put 2 in front of the sine t and 3 in front of the cosine t? Basically, you will see I multiply the x by 3, the y by 2. If we eliminate the parameter first, then you will see x minus 3 is cosine t. When I square it, that's cosine squared t. Y over 2 squared equals to 1. Now, this is the equation of an ellipse. This is an equation of an ellipse with major axis going 3 units from the center and the minor axis going 2 units from the center. So kind of imagine it this way. You have a unit circle originally, right? You have a unit circle originally. Okay, you have a unit circle originally. But then you multiply the x component by 3 and then the y component by 2. So you see what happened is you stretch this by factor of 3, you stretch this by factor of 2. Okay, so the 3 in front of the cosine stretch the cosine and therefore stretch the curve horizontally by a factor of 3. And the 2 in front of the sine for the y stretch the curve vertically by a factor of 2. By the way, in this calculus class, one of the questions that they ask is find the area of an ellipse centered at origin with major axis, major radius A and minor radius B. Find the area of this ellipse. Now, remember in my calculus, in my syllabus, I said that I suggest you to have Howard Anton's calculus textbook, because Howard Anton gives you a very good explanation on how to do this problem without using calculus at all. What is the area of an ellipse with major A, minor B? The area is equals to pi AB. What's the logic? The area of a unit circle, is pi 1 squared, right? It's pi. When you stretch that by factor of 3 left, right, then the area becomes 3 pi. When you stretch that by factor of 2 up, down, the area becomes 2 pi multiplied by 2. So the area of this ellipse here is actually 6 pi. Bang, done. No calculus. Now, let's go further. What happens if, using that, I do the following? X equals to 2 plus 3 cosine t, and the y is negative 4 plus 2 sine t. You will see that cosine t, if I isolate the cosine t, will be x minus 2 over 3. And sine t will be y plus 4 over 2. So x minus 2 over 3 squared plus y plus 4 over 2 squared, that's equals to 1. That's the equation of the same ellipse, but you translate that 2 units to the right and 4 units up. 4 units down, I'm sorry. Two units to the right, 4 units down. Now this is the center. Now this is the center. And then horizontally, you go 3 units to the left, right. 2 units up, down. So the same ellipse that we have earlier, the difference is the center has now changed. Okay, and it actually moves this way. That's the direction. Okay, let's do more problems. I open a new page. Let's call this 10.1 exercise. Let's take a look in our textbook. Maybe we do number 6 first. Number 6, the parametric function x equals to 1 minus 2t, y equals to 1/2 t minus 1, where the t is between -2 to 4. What I plan to do is, they tell us to do it first by plotting, and then second by eliminating the parameter. What I will do the parametric elimination. Okay, I will eliminate the t instead. Let me have, it's y plus 1 times 2 equals to t. I put that in there, x equals to 1 minus 2 times t. So x equals to 1 minus 4, y minus 4, x equals to -4, y minus 3. How to graph this? The x-intercept 0, -3, I'm sorry, -3, 0. When y equals to 0, x equals to -3. When x equals to 0, y equals to -3, 4. So I know that's linear, so that's why I graph it that way. I just get 2 coordinates, find the x and the y intercept. Now the thing is, I draw the line here while you see from the domain of t, that the t is actually limited from -2 to 4. Okay, so let's see, when t equals to -2, when t equals to -2, where is that located? X equals to 5, the y is -2. 1, 2, 3, 4, 5. That's when t equals to -2. The one in red is the full line. Later on, I will try to find the section just for this domain of t. Okay? t equals to, oh yeah, that's right, t equals to -2. Why I wrote -5 there? T equals to -2. And then when t equals to 4, when t equals to 4, the y will be negative, the x is -7. The y will be 1. Is it right? Yeah, that's right. So the coordinate t equals to 4 is here. Okay. Now this equation, let me use this one, actually give us the whole big line. Okay, but the domain t from -2 to 4 only give us this section. Only give us this section. Okay. It gives us the total will be a segment instead of a line. A line has no boundary. Like a line means it goes indefinitely far. Okay, it goes indefinitely far. But a segment has initial point and terminal point. Okay, so my technique is I do the parameter elimination first. I eliminate the parameter. And then I look for the initial and terminal points. Now, even though to do that, you need to be a bit careful. Okay. As for number 6, let's see number 10. The x is t squared, the y is t cubed. So we can say x cubed equals to y squared. Is it right? Don't do square root. Don't do square root. If you want to do square root, then you need to put plus minus. And it becomes not, it's harder to graph. I think if you really want to, then you do cube root instead. Okay? If you want to, you do cube root instead, because cube root is 1 to 1. I'm sorry. Yeah, cube root is 1 to 1 function such that x equals to y to the 2 over x, or 2 over 3. Then you graph that from x as a function of y. Okay, so when y equals to 1, x equals to 1. When y equals to 8, x equals to 4. X equals to 4. It's very far up there. Both have 0, 0. Notice that the x will always be positive, the y may be negative. Right? The y may be negative. So I don't really recommend to do it this way, bro. I don't really recommend to do it this way. You can, but I don't recommend that. Okay. Anyway, you will see the graph will approximately look like this. Doing it this way, you can do it this way. Y equals to plus minus x to the power of 3/2. So it follows x to some exponent, right? X to exponent greater than 1. That's why it is increasing, right? If it is square root, for example, it's still increasing, but it's concave down. Because the degree is more than 1, then it is concave up, but then you have the plus minus. You see? Okay. Now then let's start with when t is 0. When t is 0, it's here. This is when t equals to 0. When t equals to 1 is here. When t equals to 2, it's up there. It's when t equals to 2, the coordinate is 4, 8. Now the thing is, what happens when t is negative? Let's say t is negative 1. Then it will be 1, negative 1. There will be 2. This is t equals to negative 1. I don't get color. When t equals to negative 2, it will be somewhere down here. And so I'm supposed to use red color. So this is the coordinate 4, negative 8. That is when t equals to negative 2. Okay, so the direction of the curve will be going this way. Number 12. Number 12, x equals to 1/2 cosine theta, y equals to 2 sine theta, where the theta is from 0 to pi. So you see cosine theta equals to 2x, sine theta equals to y over 2. So 2x squared plus y over 2 squared equals to 1. This is x squared over 1/4 plus y squared over 4 equals to 1. That is an ellipse. Okay. 2 units up, down. Center at origin, 2 units up, down. Half unit left, right. So the ellipse approximately looks like this. Approximately looks like that. So this is half unit here, this is 2 units here. But then, how about the direction, the starting point? When theta equals to 0, you start here. This is when theta equals to 0. When theta equals to pi, you are here. Okay. So the curve is only this part. Not the full ellipse, it's only half the ellipse. Okay, because of that limitation here, because of that. Number 14. I basically do all even numbers, huh? Kind of boring. Number 14, x equals to e to the t minus 1. Y is e to the 2t. Okay, then e to the t equals to x plus 1, right? And y is e to the t squared. So this is x plus 1 squared. So the graph is approximately parabola with vertex 0, -1. Approximately, this is the curve y equals to x plus 1 squared. Okay, that's the curve. But always check with your original situation. Always check with your original parametric equation. Notice that when t equals to 0, x is 0, y is 1. This is when t equals to 0 here. Okay? When t equals to 1, then somewhere here. Now, but notice that when t goes to negative infinity, it will never reach x equals to -1. Never. So the curve is actually like this. Not the full parabola, only half of that, and it's not including the vertex. Okay? In other words, limit of t going to negative infinity of this x comma y will be -1, 0. Okay, but the range for x will be -1 to infinity, not including -1. The range of y is from 0 to infinity, not including 0. So not including the endpoint. It's not a, first of all, it's not a full parabola. Second, it's not even including the vertex. Okay, if we look at the timing, then as we go there, it goes a lot faster, but it takes you forever to reach that. It takes you forever to reach that -1, 0. I mean, it goes to that, it gets closer and closer, but never touch that -1, 0. It's kind of strange, huh? It's like some people can go really fast there, but cannot even travel these for the rest of his life. Huh? Right? Okay, you may say, oh, you know what, Thomas, the distance from here to here is further than the distance from here to here. That's true, but with your parametric equation, it will be faster for you to move that distance there instead of this little piece here. Okay, so sometimes it's not about the path. It's not about the path that you're going to go through in your life, but what kind of equation you actually use to go through that. Okay, let me give you a little break. Let me give you a little break. Some little illustration about how education can help. My auntie, the one who actually inspired me to tell me, let me stop that. Let's continue. We are done with this, number 12. Actually, no, number 14. That's the story. Let's look into question number what that we did. Number 6. So question number 6, I go to 2 factors. That's 2-dimensional factor, x, y equals 2. And then it will be 1 minus 2t. The y will be 1/2 t over 2, t t over 2 minus 1. Thomas, that graph doesn't look like what we had earlier. Oh yeah, that's right, because it has something to do with the parameter here. You see the parameter t is only from 0 to 1, right? We want the t to be from -2 to 4. So I will change this to -2 and this one here to 4. That's what it looks like. How about number 10? Number 10, I have t squared for the x and t cubed for the y. Now, they don't tell us anything about the t's, so the t will still run from, let me zoom out, you see? The t will still run from t equals to -2 up to t equals to 4, but it's supposed to be a lot larger. Right? Let me make it -20 up to +20. If you zoom it far, 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 far away, very, very far away. So you basically look at this curve from the moon, from very far away. Okay, that's what it looks like. Until when you zoom it, oh yeah, you know what? The details is here. Right? By the way, everybody look cute if you see it from a straw, the whole of a straw. Okay, number 14. E to the t minus 1 e to the t. Y actually the one on the top is t e to the t minus 1. You see, so it is in line to what we have, right? Okay. Notice that even though my t starts from -20, let me zoom. You see, it doesn't really touch that -1, 0. It's very close to it, but it doesn't touch. Actually, it stops somewhere to confirm what we mentioned earlier. I super zoomed this already. Let's see if I can trace this. I can trace this. So suppose I move this tracing. It stops here. It stops there. It's not going to here. It stops here. Right? I cannot move this further to the left, can I? Oh, I can. You know what? Let me zoom it further then. I really dig in here. That's because I use -20 here. If I use -2 only, I can see that it's not touching. Negative 1, now I'm a bit too far. Make it negative 5. Still not visible. Negative 10 maybe. Still not visible. Now it's visible. Negative 5. It stopped here. You see that? It stopped there. That's for number what? Number 14. How about number 16? Number 16, we have x equals to square root of this one. I need more skill. Keypad. First, square root of p plus 1. And for this guy here, root of p. That's what we have. Okay, the thing is, Thomas, why is not touching square root of 2 comma 0? It has something to do with the weakness of this software. Yeah, but it's supposed to be when t equals to 1, it's supposed to be there, right? Why doesn't touch it, Thomas? Maybe I change this then. Would it be better? Yeah. Okay, that's what it looks like. Compared to, the good thing about this, we can graph another equation. Say a new equation, x squared minus y squared equals to 2. You see that now? Okay, the color is supposed to be yellow. Let me change this. Let me change this to yellow. Now you see, the yellow one is the hyperbola, right? Okay, the purple one is only this part. Okay, that's for number 16. Now I would like you to, I will stop here. I would like you to actually work on your some graphing in this section 10.1. Okay. So suggested homework from 10.1 is number 5 to number 15 is good enough. Number 5 to number 15. Those will be all points. Now on Monday, then I will go on with 10.2. And next week we have a test, right? Don't forget. Okay, and it will be Zoom proctor. So please take a look on my announcement 1. How will the proctoring be done? Okay, that's for today then. See you Monday.